Hi, I am John Junyoung Chung from the University of Michigan. Today, I am going to present you the project that investigates an approach to allow scalable visual communication from viewers to the streamer in a live streaming setting. This work is done as my internship project at Adobe with great collaborators including Valentina, Haijun, Lee, and my mentor Rubaiyat. So live streaming is on the rise with expansion in the number of users and platforms. The domain is also expanding from gaming to creative live streaming and knowledge sharing. One of the key components of the success of live streaming has been the interaction from the viewers. Traditionally, user chat message has been the main way of viewer communication. However, as live streaming is visual in its medium, viewer communicating through visual means have been considered as an opportunity. Existing commercial systems and previous research systems have shown the value of it, showing that visual viewer input can allow viewers to have richer communication. However, there is a challenge in using viewer visual inputs in scalable settings, as many viewer inputs can easily overload the information channel. While there have been some approaches to handle the scalability issue, but they were either limited to simple visual inputs, like clicks on the video, or only worked for a limited set of live streaming settings. So our core question was how we can support more flexible and scalable viewer visual communications in live streaming. To understand the problem better, we conducted formative interviews and identified 4 design goals. First, allow viewers to have more flexibility in expressing visual input. Second, collect relevant viewer inputs and present them in an easily understandable way. Third, visual inputs should be easy to make so that viewers can participate without hurdles. Fourth, allow streamers to adapt to diverse live streaming settings. For more details about the formative study, please refer to the paper. Based on these design goals, we introduced a framework to design scalable viewer visual communication systems, Visual Input Management Framework, or VIMF. VIMF considers each viewer visual input as a combination of visual attributes which can be used to convey information. For example, position, shape, rotation, size, or color of visual input can be used to convey certain information. With these visual attributes, VIMF first allows streamers to specify these visual attributes in viewer input. Let us explain with an example case. If a streamer wants viewers to annotate the force of friction applied on the box, the streamer might want viewers to only draw an arrow. So the streamer can set the shape of the visual input to the arrow. However, for the position, rotation, or length information, the streamer might want users to freely place arrows with these aspects. Then for the other aspects, the streamer can impose no restriction. The system with VIMF then collects viewer inputs from viewers with these restrictions. The second feature of VIMF is to aggregate viewer inputs according to visual attributes that are critical. In the example, the streamer might think the most critical information is the rotation or direction of the force and the length of the arrow, the magnitude of the force. In this case, the streamer can only choose these visual attributes and cluster viewer inputs only considering those aspects. Third, the streamer can visualize these aggregated viewer inputs so that both streamers and viewers can better understand the collected inputs. The streamer can combine this visualization closely to the underlying video so that it can be more effectively conveyed. In the example, aggregated viewer arrows can be placed on the box, more clearly explaining how viewers actually have submitted their visual inputs. So this is the basic framework, and based on this, we designed the system BizPol. BizPol focused on specific visual attributes that are about single static objects. Hence, it only focused on visual attributes of shape, color, size, rotation, and position. It was also designed to have turns when users are allowed to make visual input so that streamers can more easily manage viewer input. Moreover, streamers could save their configuration of visual attributes, aggregation, or visualization. They could also use templates so that they don't have to do configuration interactions while they're doing streaming. For more details on how specific interaction can be done in BizPol, please refer to the paper and the accompanying video. We demonstrate that our system can be used in various application scenarios from education to creative live streaming. With BizPol, we conducted a preliminary evaluation with 3 streamers and 43 viewers. We could find that streamers use BizPol according to their live streaming context while allowing easy and expressive visual interactions with viewers. Moreover, streamers found values in aggregating and visualizing viewer inputs, as they can help understand the overall viewer inputs while further engaging viewers into the streaming. In this paper, we introduced a new opportunity to use visual communication with expressiveness and scalability in the live streaming. We hope that this work can inspire HCI researchers to further explore multimodal communication channels.